Boom, there we go. Good. All right, so we're going to get started. Try to go through an entire curve sketching problem. See how, again, in the first discussion, since I'm going to be kind of belaboring every step, it does take a while, but as we go through, hopefully when you're working on your own and whatnot, you'll move a lot faster, of course, okay? But let's start to look at an example. First example, of course, we're going to work with a polynomial. Information that might not be too terrible to graph actually, but seeing hopefully how we can incorporate a lot of those steps. All right, so let me switch to my .cam. In section 4.5, we should see my screen now, or the .cam as usual. 4.5, our curve sketching, or kind of like our guidelines for curve sketching. That whole information about using as much detail as we can without jumping to the calculator to get this information to sketch our curve, okay? And for example, to go through these guidelines, all right, just the directions it says, right, use the guidelines, meaning all those statements, A through, what was it, G, all right, use the guidelines of curve sketching to graph the equation, graph this function, and in this problem, I'm going to zoom in a little bit, get that writing a little bit darker. All right, but let's look at this problem. Try to do something interesting. Let's do, I guess, number 6 is not too bad. Number 6 on page 321, maybe something similar to that quiz we had over the weekend. All right, so this equation, page 321, number 6, y equals x to the 5th minus 5x, right? And that one probably wouldn't be too bad to graph, even using our old pre-calculus discussion, right? Odd degree on this polynomial function, so we can identify that end behavior, right? That information. We can do a little bit of factoring, find the intercepts, but let's look at this more in this kind of calculus context for work we've been doing, okay? All right, so these guidelines of curve sketching, those statements, right? So for part A, we're talking about the domain, okay? So what x values can we use, right? Along our x-axis, above what values are we going to actually have points defined? But again, with that equation, since this is a polynomial, we know that it's defined or continuous in our words with calculus, right? No holes, no jumps. It's defined everywhere, right? For all x. Okay, I'm going to zoom in here. So its domain, that entire number line, all real numbers, or that interval from a negative infinity to positive infinity, right? Really what we're doing with this step is just keeping track, looking out for any places where this function may be undefined, negative under square roots, 0 in denominators, so on. So that way when we start to approach graphing, we know something weird's happening at those locations, okay? All right, and I forgot about those problems I mentioned yesterday, accumulating all that data and information to graph, just launching right in, but we can do one of those as we summarize some work later, okay? All right, so getting back to this problem though, there's our domain. The next big piece, right, was our intercepts. Okay, so again, so far when we start, it's just more so a matter of dealing with these algebraic kind of discussions. We want to get a couple key points for our graph, okay? And so for our intercepts, we break it up into our two varieties, right? let me start off with the y-intercept. Is just a little bit faster, right? Our y-intercept is always be singular, only one. We're going to compute y with x equals 0, right? Your function evaluated at 0. When x equals 0, what happens to the y? So our equation, y equals x to the fifth minus 5x. Of course, I know it may be a little redundant, but just so we see that direct action, plugging in 0, 0 to the fifth is still 0. 5 times 0 is 0. Y equals 0 there, right? So we're getting our graph is going to pass through the origin, right? When x was 0, the y is 0, x 0, y 0. So we pass through the origin. Okay, that's the only place we cross that x-axis or the y-axis. Pardon me. Now for our x-intercepts, all right, we're going to solve that equation, taking our equation, your function, and setting it equal to 0, right? So just bring in that function notation as well. So again, purely algebraic at this stage, right? Taking our equation, x to the fifth minus 5x, setting that equal to 0. Solving here, I'm going to factor x to the fourth minus 1. Still equal to 0. Let me not forget. Oh, sorry, it's equals 5. Sorry. Make sure I get my information. I'm thinking my derivative. X to the fourth minus 5. That factors there. Boom. So in this case, I can't factor that anymore. Unfortunately, I was looking for a difference of squares, but 5 is not a perfect square at all. But we can take that 0 product property, that 0 factor. We're multiplying these two together to get 0. So either the x is 0, which we've already talked about. We're crossing the x and y axis. We're going through the origin. We knew that point already. But the other one, x to the fourth minus 5 is equal to 0. X to the fourth is equal to positive 5, right? Adding that 5 over. Taking this fourth root. And anytime we take an even index radical, raise that power, that plus or minus comes in the fourth root of 5. And that's going to be some weird decimal number, right? I know I'm trying to go away from the calculator, but just so we can kind of see it, let's calculate that 5 to the 1/4 power. Okay, and so this is going to be approximately negative 1.5 and positive 1.5, right? It's a longer decimal. Calculating that 5 to the 1/4 power, the fourth root, okay, this long decimal. But again, we're trying to get away from that because I would just estimate where that would be. I would just kind of blindly place that. But just so we have some points, right? So in this case, though, we're getting these 3 locations. One we already kind of had, where we're going to touch or cross that x-axis. Okay? All right. And hopefully as we go along, these solutions might be a little bit cleaner. But in real life, right, we're not always going to get nice integer rational values. We might get these weird radicals. You're just making sure we take our time with those. Okay? But again, we're just trying to figure out some points, some locations where we have some facts where we're crossing the y-axis, where we're touching or crossing the x-axis, okay? And we can start to see those. All right. And so then one last bit here. And again, as I mentioned yesterday, most often I kind of skip this discussion. Part C of that discusses our symmetry. Okay? And symmetry, we're just going to compare our f of x with what happens when we have f of negative x. If everything looks the same, then we're going to have an even symmetry function where it's going to be that mirror image across the y-axis. Okay? If they're opposite signs completely, that's that odd symmetry, kind of like our sine function, our x cubed function. Okay, where they're kind of what we say symmetric about the origin, flip-flopping the x and y values, sine, and so on. Okay, but let's compare, right? So for our y, that's basically your f of x, x to the fifth minus 5x. So now, when we look at f of negative x, here, boom, boom, evaluating that, this becomes negative x to the fifth power, a negative raised to an odd exponent remains negative, negative x to the fifth. I calculate that x value to the fifth power, then I know it's going to be a negative at the end. Negative 5 times negative x plus 5x. And so comparing those, definitely, if I was to, I can see between these two, I notice that all of my terms, all terms, right, are opposite signs. The signs have changed. Originally, my function had a positive x to the fifth. Now I have a negative x to the fifth. Here, a minus 5x to the first. Now I have a plus 5. So all my terms have changed signs. And that has to be true for the entire expression. So in that case, this means that f of negative x is negative f of x. So this means we have odd symmetry. Okay, and so with that odd symmetry, pushing this up, that just means that whatever happens on, right, one side of that graph, so if I want to, I can start to focus on the right side of the y-axis, right? So for all those positive x's only, I can get that information where we're climbing, falling, right, where I might have a maximum over here. This odd symmetry says that when I flip over that y-axis, all the values are going to change signs. And I'm going to have that kind of mirror image down below. I'm going to have a minimum on this side. I know it's kind of generic. I'm just kind of using my fingers drawing. But we'll see that symmetry. We'll kind of come back to it as we start to work on intervals of increase, decrease, max and mins, right? We'll see that symmetry kind of falling out. Okay. And again, that's the reason why I typically kind of skip over it, because we find it, we see it in more detailed steps later. Okay. But there's that symmetry, because if they had been exactly identical, then we would have even symmetry, kind of like a parabola, right? If one of these signs had been off, right, not exactly the same, minus x to the fifth, minus 5x, right? If this sign didn't change, then that would be no symmetry at all. Okay? So it has to be one of those two that we're discussing to involve symmetry. Okay? Periodic functions slowly but surely start to creep in, but those are for our trig functions mainly. And when we deal with trig functions, we have a different mindset for those. Okay? All right. So for part D are asymptotes. Okay, and so for our asymptotes, what we're going to see here. So vertical asymptotes, first off. Right, really, when we're thinking about these, we're thinking about more mainly, right, zeros in the denominator. Okay, but of course, with our polynomials, that's not going to happen. Right, not possible. For polynomials. So in this case, of course, there's going to be no vertical asymptotes. Rational function, we get to those, definitely will address the vertical asymptote discussion to see what direction, what our behavior is near those vertical asymptotes. For horizontal asymptotes, right? This is also kind of addressing our end behavior of our graph, right? We're taking those limits as x goes to positive, negative, infinity for our equation for our function, okay? And so now with that said, taking our equation and looking at our limit, right, we can separate these as we go to positive infinity for our function, our equation, x to the fifth minus 5x, okay? Looking at this, and maybe some work here, right? Because we have x to the fifth minus 5x, that's kind of infinity minus infinity. We don't know they're going to cancel. That's another one of those special forms or indeterminate forms, right? But if I look at it in this context, okay, do a little bit of factoring. This is x times x to the fourth minus 5, right? If I look at it in this context, when I take this limit as x goes to infinity, that x, that's going to go to infinity. Let's put this little equal sign in. Okay. X to the fourth minus 5, that's going to go to positive infinity, right? Positives throughout. And we multiply a really big number times a really big number, that's just going to stay that positive infinity, right? So kind of thinking about that context, this x to the fifth is definitely going to take precedent, it's going to dominate, right? Even though that 5x is going to infinity, it's growing without bound. It's not going to grow as quickly as x to the fifth. So that subtraction isn't going to cancel out. It's not going to create some weird balance to settle down to a singular value. Okay, and if we go back into section 4.4, L'Hopital's rule discussion, we'll see sometimes those subtractions. They'll mention how to manage those as well. Okay, but again, it doesn't come up too often, and we can kind of resort to this discussion to help us guide us through. All right, and so we also want to see what's happening at negative infinity. I'm going to actually separate out those two limits. If I do again that bit of factoring, negative infinity, let me keep my negative sign, sorry, x times x to the fourth minus 5. So when I start to do that, now thinking about that sign, this x, making it more and more negative, it's going to go to negative infinity. X to the fourth minus 5, still a really big number, but positive. And so when we see that multiplication, negative times positive is still not going to cancel. It's still going to get really large, but that negative sign is going to carry over negative infinity. Okay, and so again, this probably ties back into some discussions we would have had back in pre-calculus. But what we kind of identify with this end behavior, we're not settling down to a horizontal asymptote. There's not one single number that our y approaches, but instead our graph on the left side, as we go to negative infinity, is going to be going downwards. As we go to positive infinity, we're going upwards, right? And so again, tying back into our equation, if I sneak up here with that polynomial, an odd degree for our polynomial, right? Odd exponent on our highest degree polynomial term means we're going to go opposite directions on either end. Positive coefficient up on the right, down on the left, right? So we're kind of getting these images. And so now, just like we would in pre-calculus, right? We have our end directions, we had our x and y intercepts. So already we can start to anticipate what that graph is going to look like, what it's going to do. Okay, hopefully. But we're going to continue on. So there's part D. Now we start to bring in our calculus, right? So for part E, intervals of increase and decrease. Okay, so for our intervals of increase and decrease, that is our first derivative, right? So if our y, x to the fifth minus 5x, y prime, 5x to the fifth minus 5. Okay. And now we're going to look for our critical numbers, right? So our critical numbers, where our derivative is equal to 0, is never going to be undefined, right, with that polynomial. So taking that step, 5x to the fourth minus 5 is equal to 0. Factor out that 5. 5 times x to the fourth minus 1. That's 5. We could have divided both sides, right? The 5's not going to affect us. But definitely that x to the fourth we need to work on, right? So there's where that difference in squares I was thinking about earlier. X to the fourth, right? X squared squared, 1 squared. So we can factor that as x squared plus 1, x squared minus 1. One more time here, x squared plus 1 we can't do anything with. That's sum of squares, but x squared minus 1, x plus 1, x minus 1. So another difference of squares routine to start to factor. Okay, then once more. Right, so laying out that work, let me move this step out of the way. Okay. So now we have these different factors, right? 5, that's not going to give us any detail. Looking at this one, that's going to give us x squared equals negative 1, right? And those are our complex or imaginary solutions, which we can't graph in our real coordinate system, right? So we can forget about that. Okay, not applicable for us. We can't put that on a graph. But definitely these two, x plus 1 equals 0, x equals negative 1. There's one critical number. We're anticipating the entire domain. There's no restrictions here with that polynomial function. So at x equals negative 1, x positive 1 are two critical numbers. Okay? And so then, with our critical numbers, I know I'm moving kind of fast, I'm trying to get through some of the graphing work, okay, folks? But hopefully a little bit of recap from what we did back in section 4.3. Now taking our number line, our critical numbers down here, the two critical numbers we have, negative 1 and positive 1. Looking at the sign for our derivative, f prime, or I guess I should say y prime, right? Our derivative is 0 at these two locations. The whole point of us creating those critical numbers, how we define those. And now we need some test values, right? So some test values in these different regions, some number less than negative 1, negative 2, between negative 1 and 1, right? 0. There's no harm in using that x or y intercept as long as it's not a critical number. Bigger than 1, like positive 2, right? And so when we look at our y prime, that 5 times x squared plus 1, x plus 1, x minus 1. Moving this up, right? Looking at our terms, that 5 always positive, x squared plus 1, x squared positive, no matter what, plus 1 just getting bigger. So these two are both positive. The only ones that we really have to worry about are these two factors, right? These are positives, going to stick around. These are the ones that we have to identify, right? So at our two critical values, we have 0 for our derivative. Now in between, on either side, we're going to check. So for that first test value, negative 2, y prime, and again, for this first one, I'll keep those two positives. But now let's see this. So when I plug in -2 here, -2 plus 1, negative. When I plug in -2 here, -2 minus 1, still negative, right? So in total, positive, 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 times negative, negative, times another negative, right? So two negatives go back to positive. So up here, we're positive, we're increasing in this region. Then with x equals 0, our derivative y prime okay, positive, positive. So now at 0, 0 plus 1, positive, 0 minus 1, negative. Multiplying those through, all positives, then finally a negative at the end of that calculation, right? So on this side, we're decreasing, right? So climbing up to a maximum, right? For our next step, dropping down. Then of this side, we kind of anticipate, well, anticipated changing sign again, but we need to be careful here. Positive, positive, right? So there's the 5, the x squared plus 1, and now x plus 1. So when x is 2, 2 plus 1, positive. Over here, 2 minus 1, still positive, right? So all that together, all positives here. So we're increasing on that side. Okay? So let me borrow that discussion. Let me slide one more paper down, sorry. So with that calculation, I'm going to copy down that work. And we add here, positive, negative, positive. Okay. Our work down here. Moving that back up. There we go. So in this case, for our equation, okay, we see here we're increasing on these intervals from negative infinity to -1. And then also, I'll say union here, from 1 to infinity. Right, where we have a positive derivative, we're increasing. We're decreasing on this interval, only location where we're negative, right? Obviously between those spaces where we're increasing from -1 to 1. Okay, so there's that letter E component. So 1 there, trying to make it not look like a L or something else, okay? So there's that work. And then while we have that look to it, push this up some more, move this out of the way, I guess. While we have that, definitely directly tied to that letter F, right? Our extrema, our max and min values, right? And so with those two critical numbers, where our derivative was negative, we saw that we were increasing this side, decreasing there, decreasing, then increasing, right? So looking at that, our first derivative test, if we're going from increasing to decreasing, that means we're going to have a maximum when x equals -1. we're going from decreasing to increasing. We're dropping down, climb back up. We're going to have a minimum when x equals +1. Okay? And again, we want to get those points on our graph. Go back into that original equation. Original function there to get the y coordinate, right? And so for our maximum, we'll talk again about the fact that since our graph is continuing to increase at the end, that this maximum is just going to be a local max, right? Because our end behavior, we know we're going to climb to positive infinity. So there's going to be points later that are higher than this. So this is just a local max. Okay, and we'll talk about that on our graph as well. Same thing for that minimum. That end behavior starts to come into account to address those statements, right? But -1 to the fifth, -1, -5 times -1, +5, -1 plus 5, 4. So our maximum at -1, 4. That symmetry discussion comes in again. At +1, I'm going to guess is going to be at 1, -4. Right? Because if I play a +1 here, changing that sign, these signs change. 1 minus 5, -4. Right? So that symmetry we start to see here that our minimum at +1, -4, that solid location. All right, whatever happened on this side of x equals 0, that negative side of the x-axis, we're going to kind of flip it over, invert it, and get that mirror-like image, that mirrored reflection on the other side. And that's that odd symmetry. Okay? All right. Okay? So there's that max min. Looking at those intervals of increase, decrease. Okay? So then, the last piece, the last calculus talk before we put all this together in a graph, letter G, right, are intervals of concavity, or basically our concavity discussion, using that second derivative. All right, so if our equation is x to the fifth minus 5x, our first derivative, zoom in a little bit, 5x to the fourth minus 5, right? But then we need our second derivative to talk about concavity. 4 times 5, 20, x cubed. That constant 5 drops out. So it's just a singular term, a monomial, right? So in this case, we look for our possible inflection points by looking at where that second derivative is equal to 0, right? That's where our concavity can change, okay? And in this case, with our second derivative, it's just simply 20x cubed equal to 0. Divide both sides by 20. I know this is probably overkill, but that simple x is 0, right? That's the only way to get a 0 out of that monomial term. So in this case, looking at that location of our possible inflection point, our sign of our second derivative, right? Our derivative 0 here. But now when I start to look at, okay, and again, we can use the same test values on either side of that 0. When I plug into my second derivative, All right, negative 2 cubed, negative 8 times 20, negative, right? When we look at that positive 2, all positives here, so of course that's going to be positive. Right, so in terms of that second derivative where we're positive and negative, that addresses our concavity. We're going to be concave down here. We're going to be concave up where we're positive, right? So just be more formal. Our intervals of concavity. Let me write that title down here, and then I'll slide this up, okay? With we're using that second derivative. We're going to be concave. And again, no preference here. I'm just working left to right. Concave down from negative infinity to 0, right? That's where we get that 0. That's where that concavity switches. And we're going to be concave up from 0 to infinity, positive along that side. All right. And then because we indeed do change direction of our concavity, for our inflection point, right? As I mentioned before, we're going to use our original function, original equation. Anyway, we had the x equals 0. We've already calculated that, but just to reinforce, we're getting 0 there, pushing that up real quick. So our inflection point, the same as our y-intercept, as one of our x-intercepts, the origin 0, 0. Again, we'll kind of race through those different steps and getting those components, those different attributes. Okay. But now we're going to kind of put that all together to create this sketch, this graph for that equation. Okay. And again, as we start to deal with some more complex equations involving rational expressions, exponentials, logarithms possibly, right? Those facts will be coming in a little bit more handy, okay? All right, so now here's all the info, all the detail we've collected, right? So rather than just cycling through those pages, which of course we can do, let's start to think, right? So our domain, we're going the entire number line. For our intercepts, right? The y-intercept, 0, 0. X-intercepts at those locations, right? Negative 4 through to 5, 0. The origin 0, 0, and then the positive 4 through to 5, that 1.5 that I kind of computed, right? We had odd symmetry. Okay, all right, so looking at some of these pieces. There was no vertical asymptote. Okay, no vertical asymptotes. For that end behavior, I'm going to slide this up. All right, so there was A, B, C, D. Okay, well, I guess these two are going to come together. And then there's no horizontal asymptotes, but we did see that limit as x goes to negative infinity for our equation went to negative infinity. And likewise, that limit as x went to positive infinity for our equation went to positive infinity, right? So we started talking about having that glimpse of our graph that on the ends, we're looking like that. Okay, that end behavior component of it. Then, now the calculus showed up, right? So we were talking about our graph increasing from negative infinity up to -1, and then also from 1 to infinity. We were decreasing from -1 to 1. And with that, we had a maximum at that point, -1, 4, and a minimum at 1, -4. Okay, that's where our derivative was positive. This is where our derivative is negative. And then lastly, our concavity, we're concave down, negative infinity to 0, concave up, 0 to positive infinity. And we had that inflection point at the origin 0, 0. All right, so there's our different components that we had dealt with. Okay. Now summarize on this page. So as we start to use that, kind of like we had done up here, all right, we can start to, create our sketch. And then it doesn't have to be perfectly balanced, perfectly scaled, but we're going to try to use some of those components. All right. So I'm going to push some of this up, I know. All right. Mainly focus on this derivatives work, right? But some of those pieces of information we had, we're going to use the entire number line. We had intercepts at the origin. There's my y-intercept, the one point that I have on my y-axis, right? My two x-intercepts. There's my -4 through to 5, positive 4 through to 5. Later on, we know we had those key points, those key values at -1, 1, those critical numbers. Okay. With y coordinates at 4, -4. Okay. So starting to put in some of those values, those points, we had a maximum at -1, 4, a minimum +1, -4. Sorry, I switched my sign by accident. There we go. Okay. There's no other x-intercepts beyond that 4 through to 5, -4 through to 5. So I'm not going to cross again. All right. There's no horizontal asymptotes I'm going to level off to on either end. With that discussion, as after we, or before, or as we approach that x-intercept, right, our graph is completely going downwards on that side, backwards. Or likewise, we can see here, we're increasing from -infinity to a -1. All that span, we're going upwards. Okay. Then also bringing on that concavity, we're concave down. So we're arcing downwards. So it's not going to be able to kind of open up at all. It's going to stay closing down, right? And so for our graph, reaching that maximum at -1, +4, right? So there's our increasing going upwards, concave down, still concave down until we reach that 0, right? So I reach that maximum, start to drop down. And I know my scaling is a little bit off, but concave down throughout. And then at that 0, now we're going to flip over. Now we're going to be concave up, opening upwards, dropping down to the minimum, right? So there, between -1 and 1, we're decreasing, going downwards. Then after I reach 1, now I start to increase, right? So out of there, we're climbing upwards, still concave up, continuing to be concave up, increasing beyond, right? So these are just going to be local max, local min, because that graph is going to continue to go downwards, continue to go upwards beyond, right? And there's our graph for that equation, that function, right? Definitely a lot going on there with such a simple function, if you will, right? Just this two terms binomial, but kind of going through those different details. And so, of course, when we start to see some of those rational functions, functions that involve products with a little more interesting, complex functions, expressions, having to deal with those concavity and the first derivative increasing, decreasing, those calculations will be a little more time consuming, of course, but hopefully a little bit more fruitful in identifying, okay, what that graph's going to look like, okay? And so tomorrow we'll have our class meeting again via Zoom, and we'll try to pick out one of those examples that incorporate either a rational function or something a little bit more complex beyond a polynomial to incorporate these facts, these ideas, okay? All right, but there's our steps, so A through H total, A through G, all the calculations and work, and then H is putting it all together to make our sketch. Okay, right on. So we'll take that, and again, I'll try to dig up some of the problems I've done before in previous courses, and I'll try to post those for you guys so you can kind of see that walkthrough as well. But we'll try another one tomorrow. All right, crew. All right, thanks for showing up. We'll see you tomorrow right here.